There are some limits that all the techniques we've discussed so far don't work. So we need some more tools, new, different kinds of tools, because they are new and different kinds of problems to be addressed. One of the tools we're going to develop is something called the squeezing theorem. I had an instructor in graduate school. Sometimes he called this the sandwich theorem. You'll see why here in a bit. The squeezing theorem. I'm going to just tell you what the squeezing theorem says. We're not going to prove that the squeezing theorem works. That's a topic that's beyond the scope of this course, as they say. But I'm going to state the squeezing theorem, and then I'm going to go through a demonstration of how it gets used. I want to be very clear on this, so make sure you have this piece square in your mind. I'm not going to ask you to state the squeezing theorem. I'm not going to ask you to prove the squeezing theorem. I'm not going to ask you to use the squeezing theorem. What I am going to ask is that you become familiar with the squeezing theorem. We will use it later in our course. You tend to use it in Calc 2. It comes into play in Calc 3 in places. It comes into play in various topics as you go through the curriculum, as you go through the coursework. If you hang around long enough, like you're supposed to, you'll take a senior level or a graduate level, some sort of a advanced calculus course, and you'll actually go through a proof that the squeezing theorem really does work. For us, for now, what I'm after is this. You need to be able to recognize the squeezing theorem when you see someone on this side of the camera using it. When you see someone on this side of the desk using the squeezing theorem in an argument or in a discussion or in a proof, you need to be able to say, that's the squeezing theorem. Okay, so that makes sense, so I'm following what you're saying. The squeezing theorem is a useful tool. At this stage of the game, all you need to be able to do is recognize a squeezing theorem argument when you see one. And if you hang around long enough, you'll get used to it, and then it becomes a little bit more user-friendly from your side of the camera as well. For now, this is just sort of an introduction. We're going to use it to develop a few more limits, and then we're going to merrily along our little way, and we won't see it very much. We'll pick it up one or two places again later in the semester. When we do, you'll say, oh, that was the squeezing theorem, wasn't it? Yes, that's what's going on. All right, so the squeezing theorem says this. There's a great big if and a little bitty then. So a theorem usually is if all this stuff, then this stuff. The squeezing theorem has a whole bunch of if. So you need to have a lot of stuff working. If you have all this stuff, then this little conclusion you're able to draw. So let's take a look at the squeezing theorem. It says this. Squeezing theorem says if you have three functions, and if f of x is less than or equal to g of x is less than or equal to h of x. So the squeezing theorem, you're always dealing with three functions. If you don't have three functions in this particular version of it, you're not working with the squeezing theorem. All right? It says you have three functions. F of x is less than or equal to g of x is less than or equal to h of x. Now, this is on some closed interval. So we have some interval. Here's A, here's B. And in that interval, this is happening. Outside that interval, we don't care. We don't care what happens outside that interval. But inside that interval, they behave themselves. All right? So see if this color shows up. Suppose g of x is the white. Suppose f of x is the red. And suppose h of x is the blue. All right? H of x it's like, it's goofy, but it helps you remember. Baby bear, mama bear, papa bear. Little, middle, big. And so f of x has to be down here somewhere. Outside of this interval, I don't care what happens outside the intervals. No, we don't care. And we also have h of x let's see, g of x is in the middle somewhere, and h of x is up here on top. So we got that, and that's what's happening. F is on the bottom, g is in the middle, h is on top. But then we also have some more information. And suppose we also know this. For C in the interval, so C is in the open interval AB. C is, let's say, right here. Now I'm going to change the picture, so I'm going to erase my 3 graphs. I'm going to make an additional restriction here. What I'm going to say is the limit as x goes to C of f of x, that's the red, is equal to L. Now, here's how I want to draw that. L. The limit as x approaches C of f of x is equal to L. So as you choose values on the x-axis that get closer and closer and closer to C, the values on the y-axis get closer and closer and closer to L. It doesn't need to be precisely like this, but this illustrates the point pretty well for what we're doing here. So we have that condition met. We also have another condition. The limit as x approaches C of h of x is also equal to L. What does that mean? Remember, h is the top function. G is somewhere in the middle. So h, now, watch me. Watch what I'm doing here. That's not good enough. That does not meet this requirement. Do you see that? Because as you get closer and closer to C, the function h must also approach L. And so what must happen is something along these lines. So L is sort of this purple. It's kind of both red and blue. So that's the setup. We know that the F goes to L. We know that H goes to L. And we know that G is captured in between them. I think you're starting to see why this is called the squeezing theorem. Now, this is a great big if. It takes a long time, or it takes some effort to establish all this stuff is true. But if we have all that stuff established to be true, if G is in the middle, F goes to L, and H goes to L, then is it clear what we may conclude about G? What do we know about the limit as x goes to C of G of x? What must that equal? Well, what are some possibilities? Maybe G is like this. G's in the middle, G comes in here, and then it hops up here. Why is that not allowed? That's not allowed because we've required this. Is it clear what must happen? G, the function in the middle, must also go to L. A metaphor I like to use is, remember in the rodeo when they have the bucking bronco, right? And the rider gets off and the horse is still bucking. Now, what they want is this horse whose behavior they don't know about. They don't know how this bucking horse is going to behave. But what they want is to make sure that horse goes through this. There's a gate they want to get this horse to go through. So what do? They have these 2 outside rider ponies. These ponies, they know how they're going to behave. They know these 2 rider ponies are going to go through the gate. And they also know that these 2 rider ponies capture between them this bucking horse whose behavior they want to control. And so it's the same principle. if you have this bucking horse whose behavior you want to control captured between these other two well-behaved ponies, and if I know the bucking horse is between my two horses, and my horses go through the gate, that guarantees that the bucking horse must also go through the same gate. So the blue is a rider pony. The red is a rider pony. The white is some function whose behavior we want to control. If we know the red and the blue are forced to go through this point, if we know that the red and the blue are forced to have the limit equal to L, then white, which is always captured between them, this function g of x, must also have that same limit. Now, here's how this gets used in practice. That's the statement of the squeezing theorem. I think you can see why I had a professor called this the sandwich theorem, because the white is sandwiched between them. The way this gets used in practice is this. You have a function whose behavior you don't know, but you want to understand. That's g. You need to find, now when I say you don't need to. When we were in graduate school, we needed to. We need to find these functions. And we need to guarantee that these functions exhibit this behavior, and we need to guarantee that these functions exhibit this behavior. If f and h exhibit both this behavior and that behavior, that guarantees that g must exhibit this behavior. We are leveraging the behavior of two functions whose behavior we know. We're leveraging that behavior to determine the behavior of a function that we don't know how it acts. And so that's what's happening here. That's the statement of the squeezing theorem. Now, what I'm going to do in a bit is I'm going to show you a demonstration. The next video, I will present a demonstration of we're going to have a function g of x whose behavior we don't know. And we want to know what that behavior is. We have a limit we want to find out. I'm going to create function f. I'm going to create function h. I'm going to show that this condition is true. I'm going to show that this condition is true. And as soon as that happens, then I get to conclude that this condition must also then be true. So that's the statement and an introduction to the notion of the squeezing theorem.